Hello and welcome to this clip on redox titrations. We'll take you through how we use volumetric analysis in redox titration, the key stages in the calculation that go with it, and a selection of simple examples and applications. Before going any further, it's important that you're comfortable with using mole ratios from equations. Your titration calculations from your first year available chemistry should be pretty familiar, and also principles of redox and half equations should be secure as well. If you're not sure about any of these, it might be worth stopping and going back over them from your first year before proceeding any further. So first, let's have a little review of how we balance redox half equations. So let's do a quick review of how to balance redox half equations before we go any further. We'll do a couple of examples just to illustrate what to do. So if we start off with a simple oxidation of Fe2 plus to Fe3 plus, you can see that there's an electron lost. So I've put a partially complete reduction half equation in, and I've left some space between my manganate ion and the arrow to add things in that I need to as I go. First thing to do is to assign oxidation numbers to the manganese on both sides. The right hand side is clearly 2 plus because that's the charge of the ion. On the left hand side you've got 4 oxygens, each one is worth -2, so which is a -8 in total. So for that to become -1 overall, you need +7. So going from +7 to 2 plus, which if I'm referring to it as an oxidation state, I should really say +2. That is obviously a reduction because it becomes less positive, and it goes down by 5. So that must mean there's 5 electrons being gained. Now what I want to do is make sure that the oxygens go somewhere. There's 4 oxygens in my manganate ion. So that means I can have 4 waters on the right hand side. That now automatically means that I need 8 hydrogens on the left hand side, which takes care of the reduction equation. Now what I've got to do is balance the electrons. So I do that by multiplying the iron oxidation half equation by 5. So cancelling electrons in both equations, I have an overall balanced redox equation at the bottom of the screen. So we can do it again using another pair. Let's stick with the same oxidation, but this time we've got dichromate, or chromate 6. So we have to apply the oxidation states first of all to chromium, so then we can work out how many electrons it's gaining. So on the right hand side obviously it's a +3 oxidation state because it's the same oxidation state as its charge. On the left hand side there are 7 oxygens. 7 times -2 gives you -14. For it to be 2 minus overall, it has to be +12, but that's split between 2 chromiums, so each chromium is +6. So although at first going from +6 to +3 might seem like you should put in 3 electrons, don't forget it's happening twice because there's 2 chromiums, so we need +6e-. And because you have 7 oxygens in the dichromate ion, you have 7 waters on the right hand side, which now generates the need to have 14 H pluses on the left hand side, like so. So obviously what you've got to do is multiply up the oxidation by 6 because each oxidation generates 1 electron and the dichromate ion requires 6 electrons to be reduced. So cancelling out the electrons in each half equation, that gives us the overall balanced redox equation: 6 Fe2 plus Cr2O72 minus plus 14H plus gives you 2 Cr3 plus 6 Fe3 plus 7 H2O. So redox titration, the practical part of it at least, is carried out exactly the same way as an acid-base titration, except instead of an acid and a base reacting, you have an oxidizing agent reacting with a reducing agent, so it's based on a redox reaction. The standard solution, which is your oxidizing agent, will go in the burette, which I'm just about to highlight for you. And your reducing agent, which is your solution of unknown concentration, will be placed in the conical flask. So far it's very similar to the way an acid-base titration from your first year works. The mole ratio between them is a balanced equation that you'll have already, and the average titer that you get is used to work out the moles of the reducing agent present. The endpoint is exactly the same as an acid-base titration, except you don't need an indicator because the oxidizing agent is usually a certain colour that will change at the endpoint. So the visual change means it's self-indicating, so there's no indicator as such that needs to be added. So just to recap, the solution of known concentration goes in the burette, the solution of unknown concentration goes in the conical flask. So the average titer allows us to work out the moles used, and we use N equals C times V, just like a normal titration calculation. The moles used out of your other solution, the solution in the conical flask, the moles used of that comes from the balanced equation. We also know the volume that we put in the conical flask. So if we know the volume that we put in the conical flask, and we've just worked out the number of moles that were used, we can now work out the concentration by rearranging N equals C times V, so it's C equals N over V. So let's look at an application. A common application is finding the percentage purity in a solid sample. So the first step is to weigh your solid sample to find out how much you have. You then dissolve your solid sample and make it up to 250 centimeters cubed in a volumetric flask. And then finally, once you've done that and made it up to the mark, which will usually be indicated by an etched line on the glass on the side of the volumetric flask, you use a pipette to withdraw about 25 centimeters cubed or thereabouts, and we titrate that 25 centimeters cubed sample against the oxidizing agent in the burette. And you obviously repeat the titration until you get two or more concordant values that agree within 0.1 centimeters cubed of each other. So it's exactly the same way you do it for an acid-base titration from your first year. The only difference is it's a redox reaction and not an acid-base reaction. So one common type of redox titration is the iron to manganate titration. You can see from the colours of the transition metal ions that manganate ions have a deep purple colour in aqueous solution when they're in oxidation state 7. But when they're reduced to oxidation state 2 in Mn2+, they turn a light pink colour. So this makes the endpoint easy to spot visually. The two half equations for this redox reaction are at the top of the page. Now what you've got to concentrate on, obviously when you're balancing redox half equations, is the number of electrons. So obviously what happens is the iron 2 plus half equation gets multiplied by 5, because the manganate half equation requires 5 electrons. So the manganate half equation stays the way it is. The Fe2 plus to Fe3 plus half equation gets multiplied by 5. And I'm just going to put the overall balanced redox equation on the screen in a second. Why don't you pause the video and see if you can work it out for yourself. So you can see within the overall redox reaction there's a colour change that you can notice with the naked eye. So that means that this particular titration is self-indicating, like we talked about a little bit earlier in the clip. So let's start by doing a simple example. It's got the equation that we've just worked out at the top of the page and asks us to say what the colour change was. But we need to be careful here because it's the colour change in the conical flask as shown in the photo from the last screen. So if you look at it quite carefully, it's a sort of very, very pale green, isn't it? And it will go to purple because you can see that the manganate solution in the burette is clearly a purple colour. So now it asks us to calculate the concentration of aqueous manganate 7 ions used in the titration. So we start by working out the number of moles of iron 2 plus using the data that we have at the top, and then we can work out the number of moles of MnO4 minus, because if you look at the equation at the top, I've now annotated it the 5:1 mole ratio. So you divide the number of moles that you worked out for the iron 2 plus by 5, which gives us 0.00025. So moving to the right of the screen where I've indicated with the blue arrow, concentration equals number of moles over volume. And using the end point, the volume of aqueous manganate ions required to reach the end point, which I've highlighted as 12.30, you do the number of moles, which is 0.00025, divided by 12.30 over 1000, and drawing your attention to the fact that the answer is to 3 significant figures, it's 0.0203. Let's check the mark scheme to this to make sure we're on the right track before we go on to a slightly more applied version. So we got the moles as 0.0125. We then got the manganate moles by dividing that by 5. We worked out the concentration of manganate, including the 3 significant figures. So we got our 3 marks. Now let's try a slightly harder one. So let's have a look at a typical exam question. Usually what they'll do is they'll lay out a set of steps for you, and they'll give you a series of structured questions to work through. So you can see it's a percentage by mass, because as I've highlighted, it says percentage by mass of iron in a sample of moss killer. So we can determine this percentage by titrating it against acidified potassium manganate 7, just like we looked at in the previous screen. So in stage 1, the moss killer is dissolved in excess sulfuric acid, and this is so we can provide the H plus ions in aqueous solution needed for the reduction of the manganate. Then it says copper turnings are added to the acidified sample of moss killer, and the mixture is boiled carefully for 5 minutes. Copper reduces any iron 3 ions in the sample to give iron 2 ions. So we've got to remember that it's only Fe2 plus that actually reacts with manganate. So iron 3 ions won't actually react with manganate because they can't be oxidized any further. So this brings us to the first part of the question. I've left out the other stages just for a moment because they become relevant a little bit later on. So moving down to where it says suggest why it's important to remove all the copper in stage 3 before titrating in stage 4. So there's actually several different things you could say. Copper itself is a reducing agent because of its position in the electrochemical series compared to iron. It's lower down, so its electropotential is more negative. So basically the copper might also react with the manganate. The copper might also reduce any Fe3 plus formed in the titration back to Fe2 plus, which is what you don't want. And like we just suggested, all the iron is in the form of Fe2 plus before you start. So that's why we use stage 3 before we start the titration, is to get rid of any copper. Because the copper's job is done. We don't want it interfering with our titration in any way. So now we're at stage 4. The contents of the flask can be titrated. So let's move the page down a bit. So we can have a look at the next part of the question. So it gives us the ionic equation, and we looked at this in the last screen anyway, and it's asked to say, explain in terms of electron transfer why this reaction involves both oxidation and reduction. So I've highlighted possibly the most important parts of that statement, that request there. It must be in terms of electron transfer, and it must refer to both oxidation and reduction. And you've got 2 marks, so you've got 2 things to do. So I'm choosing to go with the manganese first of all, and I've stated that its oxidation state was +7 in MnO4 minus, and it changes to +2 in Mn2 plus, so it's reduced. The oxidation state has become less positive. It's gone down. And I've said something similar for iron, except this time it's for oxidation. So the oxidation state of iron changes from +2 in Fe2 plus to +3 in Fe3 plus. And I've said it is oxidized. And you'll notice I've put next to reduced, I put in brackets Mn. That's to clarify what I mean by it. And I've done the same for iron at the end of my answer. So then the final bit says, a student analyses a 0.675 grams sample of moss killer using the method described. Now if you remember in the couple of screens ago, we had the layout for how we did this particular practical. So this would be your solid sample that you weigh out before you make it up to 250 centimeters cubed. So our starting point is obviously to find the moles of something, just like any titration calculation. So we can use the volume and the concentration to work out the number of moles of manganate ions in aqueous solution. So that gives us 4.50 times 10 to the minus 4. But this is for 22.5 centimeters cubed. If we look back at the rest of the question, and reading it carefully, this time they haven't actually said anything about what the total amount in the volumetric flask was, but we have got is 0.675. And that 0.675 is for the moss killer, which contains iron. Now we've just worked out the number of moles of manganate, and we know from the equation that the number of moles of manganate to the number of moles of iron is 1 to 5. So that gives us 2.25 times 10 to the minus 3 moles of iron 2 plus. So I'm sticking to my calculator value to keep my accuracy up during the stages in the calculation, and I've worked out that the mass of Fe2 plus is 0.12555 grams, because I've done moles times mR. I've gone to a periodic table to find out the mR of iron. Now obviously the mass of Fe2 plus will be the same as the mass of Fe, because it's only a matter of a couple of electrons, which has negligible mass, so it's not going to make any difference at all to the mass of iron metal. So they want to know the mass of iron metal in the moss killer. So what you do is you divide the mass of Fe2 plus that you worked out in your titration by the original mass of moss killer, which is 0.675. You multiply it by 100 to turn it into a percentage, and that gives us 18.6%. If you're doing a calculation like this and you're writing on the piece of paper, don't forget to actually put your answer in the percentage answer line, just so the examiner's attention is drawn to it. So let's now have a quick look at the mark scheme to see how we fared against what they were expecting. So we said one of the two possible things for the problem of having copper present, or leaving it there. We talked about what happens to manganese in terms of its oxidation state. We talked about what happened to iron in terms of its oxidation state. We worked out the moles of manganate. We multiplied that by 5 to get the moles of Fe2 plus according to the balanced redox equation. And we worked out what the mass of iron would be using moles times mR, and we worked out what the percentage that would represent using the 0.675 grams we were told in the question. So far so good. So another application of redox titrations is the percentage of copper in brass, such as a brass coin. The problem here is that copper doesn't have as many oxidation states as iron, and its colours are not as marked, its colour change is not as marked, as you can see from the table. So what we do is we use the fact that copper can be dissolved in nitric acid to make copper 2 plus ions. And copper 2 plus reacts with iodide ions according to the equation in the box. And we use the fact that the iodine produced in that reaction will react with thiosulfate ions, which are S2O3 2-. So S2O3 2- is the standard solution. So you can see that as the S2O3 2- reacts with the iodine from the reaction in the box, it produces iodide. Now the thing about iodide is that it is a different colour in the presence of starch than iodine is. But unfortunately the change from iodine to iodide is quite a gradual change. So although they have two different colours, we use an indicator to help us this time. Now you may or may not be aware already that starch and iodine form a very deep black solution called starch iodide. So as the colour of the iodine starts to fade during the titration and it gets to around a straw colour, because it's a very gradual endpoint and quite difficult to actually sort of see visually, we add starch at that particular point, which makes the solution suddenly go a sort of dark black colour. And then when all the iodine is gone, that colour will suddenly disappear, and that's our endpoint. So let's do a typical exam question on that type of redox titration. A piece of common knowledge you may or may not have at this point is the fact that zinc is the other metal present in brass. So I'll just pop that one in, because although it's relevant-ish, it's not quite as relevant to the mechanics of the redox titration that we're talking about. So one common use for brass, we've talked about coins. You could use any use for brass, provided you're able to actually explain why that use for brass makes use of brass's properties. Now brass is quite strong and durable, so we use it to make coins. So let's now look at the analysis part. So it says, during the analysis of brass, 1.65 grams of the alloy. So I'm going to highlight that automatically, because what I'm doing at this point is just collecting pieces of information that I know will be useful and I'll need to use at some point. So in this particular question, it tells you that it's made up to 250 centimeters cubed, like we talked about a little bit earlier in the clip. This time it's given you the information, so that's going to be significant later. And like we talked about earlier in the clip, we have a 25 centimeters cubed portion. So because 25 centimeters cubed is 1/10 of 250, that means it's going to have 1/10 of the copper that's in the original sample of alloy, your 1.65 grams. So it tells you that it's been titrated with 0.1 mole per decimeter cubed of sodium thiosulfate, and that 20 centimeters cubed of that aqueous sodium thiosulfate were used to remove the iodine. Now the excess nitric acid, don't forget, was used to turn copper into copper 2+. Now the problem is you used excess, so therefore there'll be some nitric acid left that might interfere with our titration. So we have to neutralise it somehow. So it's basically testing your common sense here. You use an easily available base or alkali of some kind. Sodium carbonate or sodium hydroxide will do. It says, what indicator is used in the titration of iodine with sodium thiosulfate? And remember we said that iodine reacts with starch. We spent some time talking about that in the last screen, didn't we? So that's what we can put in here. So it's added as the colour of the iodine starts to fade. So to give a clearer endpoint than a rather slow fade from blue-black to straw, when it turns a straw colour, just add the starch at that point. So let's now move the page down. And it says that the reactions taking place will be summarised as follows. Well, we've seen these two equations already in the previous screen, and it asks you to calculate the amount in moles of sodium thiosulfate in 20 centimeters cubed of solution. So to do that, we've got to go to the top of the page and back to our information, and we have it highlighted up here, which gives us 2.0 times 10 to the minus 3. So I'm going to make sure I put that in my actual answer, like that, just to make it clear to the examiner that that's what I want him or her to consider. So I've gone on to the other side of the sheet. I've made a copy of the previous screen so we can move it around as we do the answers here. So it says, for every 1 mole of Cu2 plus ions present in the solution, deduce the amount in moles of S2O3. So what we need to do here is to use this bit here. And you can see quite clearly that it's a 1-to-1 mole ratio, because if we look at them close up, you can see that they are a 2-to-2 mole ratio. So copper to thiosulfate is a 2-to-2 mole ratio. So then, it asks us, what is the amount in moles of Cu2 plus ions present in 25.00 centimeters cubed of solution? And we can say it's 0.002, because if we take our page and we make it a bit bigger, we can see that the number of moles of sodium thiosulfate and the number of moles of copper are going to be the same. So the first thing to do when calculating the percentage by mass of copper is to work out the mass of copper 2 plus ions. Now we know that there's 0.002 moles, so we rearrange the moles equals mass over mR equation to give us moles times AR, or atomic mass, relative atomic mass. The relative atomic mass of copper, if you consult a periodic table, is 63.5, so we multiply that by 0.02, which gives us 0.127 grams. So just to keep the page nice and clear, I've circled where it told us in the previous page what the actual mass of the alloy sample was. It was 1.65. But we also need to remember that the 0.127 grams only refers to 25.0 centimeters cubed. It was made up to 250. So I've just circled that to remind you. So that means there's 1.27 grams dissolved through the sample in 250. So the percentage by mass gives me 77% rounded to the nearest whole number. So now let's have a look at the mark scheme and see what they would have wanted us to get this time. So we got the fact it was zinc, and we said it was hard wearing. We suggested sodium carbonate. We mentioned starch indicator, and we said it's just before the end point. We mentioned pale straw. We got 0.02 moles, 1-to-1 mole ratio, so therefore the same number of moles for our thiosulfate. We got 0.127 grams in our 25 centimeters cubed, 1.27 grams in 250, and therefore 77% as our final, and we got all the marks that way. So now let's have a look and see if we can pull together some of the common themes that we've looked at, so we can start to see how to think our way through any particular redox titration question they might want to throw at us in a paper.
Another important application of the iodine thiosulfate reaction that you may come across at A level is the volumetric analysis of the chlorate 1 ion in bleach. And this ion is very toxic to bacteria and other microorganisms, so it's used in toilet bleach. It's sometimes called hypochlorite, so you can see sodium hypochlorite on the ingredients list on the side of this bleach bottle in the photograph. So the first thing to happen is the chlorate ions from the bleach are reacted with iodide separately in the presence of H+ to form iodine. And this involves the chlorine in the chlorate being reduced. And at the same time, the iodide ions are oxidized. Just to clarify this as a redox reaction overall. So that reaction mixture is in the conical flask. And the sodium thiosulfate usually, can be any thiosulfate, but usually we use sodium thiosulfate of known concentration, is placed in the burette and titrated against that reaction mixture, because we're trying to work out the number of moles of iodine. So following the reaction from the beginning, 1 mole of chlorate produces 1 mole of iodine. So that means the mole ratio of thiosulfate to that iodine produced is 2 to 1. So the mole ratio link between the original reaction and the titration is that the number of moles of chlorate ions to the number of moles of thiosulfate ions is 1 to 2. So we can use this in our calculations when we're trying to determine the molar quantities and therefore the concentration of chlorate. So this is another application of the iodine thiosulfate reaction. You'll notice in both cases the thiosulfate goes in the burette, but it's not the oxidizing agent this time, it's actually the reducing agent. So right at the beginning of the clip we said that the oxidizing agent usually goes in the burette. This is a case where it doesn't. But what does always go in the burette is what we know the concentration of. Just like in any titration, your standard solution always goes in the burette. So for determination of percentage purity, you use the volume of the standard solution used in your average titer plus its concentration to determine the moles of the reagent in the standard solution needed to react. The standard solution will be in your burette, as highlighted in yellow. The mole ratio in your equation will tell you how many moles of the unknown in the conical flask was reacted, which I've now highlighted in yellow again. The volume in the conical flask that was titrated will be a proportion of the original unknown sample, as you can see from the diagram. So you have to multiply the moles in your titrated amount up to compensate for the number of moles that are actually present in your original sample. You convert the moles in the original sample into mass, then divide that mass by the mass of your original solid sample, which is that amount, and you multiply it by 100 to get a percentage. That gives you the percentage purity. So for water of crystallization, you're working out the moles of H2O. The first steps in the process are exactly the same as for doing percentage purity, except when you get to step 3, the number of moles you've worked out will not include the water of crystallization. It only tells you the moles of anhydrous salt which reacted. So, what step 3 gives you is this. Now, the number of moles of anhydrous salt is exactly the same as the number of moles of hydrated salt. The hydrated salt, which is highlighted in yellow, that contains your XH2O. So we can use this fact to work out the MR of your hydrated salt. The mass of your original sample times the moles of hydrated salt in the original sample equals the MR of hydrated salt. Now you've worked out the moles of the anhydrous salt from your titration, but that's only a proportion of the total amount. You multiply it up to work out the number of moles of anhydrous salt in your original sample. So that's where you're going with this. You want to work out the number of moles of hydrated salt. So once you've worked out the number of moles of hydrated salt by taking your anhydrous salt and multiplying it up, now you can work out the MR of the hydrated salt by carrying out the calculation that's highlighted in purple. Now if you take that MR value and you subtract from it the MR of the anhydrous salt, you end up with a proportion of the molar mass of the salt that's just due to water. That's isolating the H2O. So that isolated amount, you divide it by 18
which is the MR of water, to work out X. And that now tells you how many moles of water of crystallization you've got in your hydrated salt. So again, we've got a set of stages. And you can see a sample is added to a conical flask of known mass. The sample has 25 centimeters cubed of sulfuric acid added to it. Now that's to make the MnO4 minus have the hydrogen ions to react with. That's all that's for. Then finally, the contents of the flask are heated to 60 degrees. Because both ions are negatively charged, and to make two negatively charged things come together and react requires a little bit of extra energy. So when the contents of the flask are hot and reacting, they're then titrated against the manganate. So it says in stage 2 the hydrated crystals dissolve. It gives you the mole ratios, 1 to X, X being the moles of H2O. And it says in stage 4 the equation for the reaction is shown as below. So you can see that you've got a 5 to 2 ratio of manganate. But the first thing it asks you to do is to say what you would see. And what you would actually observe is because of the sudden excess of MnO4 minus, which as you know is purple. So you assume, unless otherwise told, that the ethane diorite is colourless. So the colourless solution will turn purple or pink. It's only what you would see that they're asking for here. So let's move the page down a bit now. So you'll see I'm leaving the data at the top so you can work with it. The first thing to do is to work out the moles of MnO4 minus that was used. To do this, I've got to identify not only the titer that was used, the volume, plus also the concentration. So that means I use 19.05 and 0.02, both of which I've now highlighted from different places in the question. And if you look closely, the question itself actually told you where to look to get the data. So 3.81 times 10 to the minus 4 moles is what I have. So by making a note of the mole ratio between COOH2 and MnO4 minus is 2 to 5. If you have a look at the equation, which I've highlighted. So we know the moles of MnO4 minus is 3.81 times 10 to the minus 4. So we can take the moles of manganate, divide it by 2, then multiply that by 5, which gives us 9.525 times 10 to the minus 4. So because the page is getting a little crowded now, I'm going to switch colours. I'm going to turn to blue. So now I'm trying to work out the MR of my anhydrous COOH2, which is 90. So to work out the MR of my hydrated salt, it's simply moles over mass. We know what the moles are, so we just divide that by the mass, which gives us 126. The difference between them is 36. Like we said in the previous screen, the MR of water is 18. 18 goes into 36 twice, which means we've got a water of crystallization number of 2, so X is 2. Let's have a look at the mark scheme to tick off what we got right. We got the colour change, we got the moles of manganate, we got the moles of ethane dioric acid, and we worked out the relative formula mass by dividing the number of moles of COOH2 by the original sample's mass, which was 0.120, I think. Sorry, the other way around, wasn't it? 0.120 divided by moles of ethane dioric acid, sorry about that, which gave us an X value of 2, because 18 is the MR of water. So this has been a slightly longer than normal clip, and there's been several applications of the redox titration method here, so I'm going to leave it here and suggest that maybe you go away and practice some examples from your textbook, or maybe find some similar examples from past papers. Best thing to do is to jot down any questions you've got at this point, because I'm sure there'll be a few. Bring them into your teacher, or maybe come and see one of us at a subject extension. In the meantime, thanks for your time. I know it's been a bit of a long one this time, and see you soon, hopefully. Thanks again.